Okay, so first of all, thank you very much for attending this ceremony. I'm very pleased and feel greatly honored by this medal. I should perhaps say, Laius mentioned it, that in 1973 I participated in the International Mathematics Olympiad, and of course you all know, in order to be successful in such Olympiads, this requires some training, and I remember in those times, in the 1970s, I had two great journals. The one was the journal Quant, it was in Russian, and the other was the Mathematica Lapok, it was in Hungarian, and at that time I was even able to read a little bit Hungarian, at least to the extent to understand mathematics, and that's usually easier than spoken language also. So anyway, I feel very honored by this medal and will try my best to entertain you with a talk now. So, yes. Let's see. The question is what to speak about at an occasion like this one. If we have a matrix and the Frobenius norm or the Hilbert-Schmidt norm is defined in this way, and this inequality is trivial. In 2005, David Wenzel, who was then a PhD student of mine, we had to deal with another problem for the commutator of matrices, and I was sitting down and starting the paper and wanted to write the first sentence, and the first sentence was, if we have two matrices of Frobenius norm 1, then the commutator can assume every value between 0 and 2. 0 if the matrices compute, and 2 if, and suddenly I didn't find a pair of matrices such that the commutator is 2. I tried it 1 hour, I tried it 2 hours, and then did what one usually does. I called MATLAB and took 1,000 randomly chosen matrix pairs of Frobenius norm 1 and computed the commutator, and I observed the maximum was actually square root of 2. Of course, this was what MATLAB told us, but we were not able to prove this. Although we spent several months to prove this inequality, we were able to prove it for 2 by 2 matrices, and even this is non-trivial, but not in a more general context. So, I'm mentioning this because this is the question, what could one become famous for? We had a problem, I could not solve this problem, but my name appeared in many papers. Laius Laszlo then proved it for 3 by 3 matrices, then 2 Chinese people proved it in the general case, and also observed that this is equivalent to a question on the curvature on Riemannian manifolds. Laius Laszlo did again one more paper on this, and in the end our inequality landed at the cover page. Sorry. It landed on the cover page of a book. So I think if something of my work will survive, it will be this inequality which we actually could not prove. Well, but now let's come to some things I could prove. Let's begin with Laurent matrices. Laurent matrices are doubly infinite matrices. Of this kind, they are constant along these diagonals. If you consider the multiplication operator by a function a on the L2 over the unit circle, then this matrix is the matrix representation of this operator on this orthonormal basis. And it turns out the AKs are just the Fourier coefficients of this function. Okay, consequently, this operator is bounded if and only if multiplication by A is bounded, and this happens if and only if A is in L infinity. So we can say such a Laurent matrix induces a bounded operator on L2C in the natural way, if and only if these numbers are the Fourier coefficients of a function in L infinity. Toeplitz matrices are the lower right quarters of Laurent matrices. That is, the Toeplitz matrix is of this form, and it follows that if the big matrix induces a bounded operator, then the smaller matrix induces also a bounded operator. That is, a Toeplitz matrix generates a bounded operators if the numbers in this matrix are the Fourier coefficients of a function in L infinity. And these matrices are nowadays called Toeplitz matrices because Toeplitz in 1911 proved that this is not only an if, it is an if and only if, as he proved even 3 words. Notation, given a function in L infinity, we denote by LA the Laurent matrix generated by the Fourier coefficients of this function, and by TA the Toeplitz matrix generated by this function. And not only the matrix, but also the operators this matrix generates on L2, and this function is usually referred to as the symbol of the matrix. Well, we are interested in spectral characteristics. If we are given a bounded linear operator in a complex Banach space, then the spectrum of A is the set of all lambda such that A minus lambda I is not invertible. And an operator is said to be Fredholm if it is invertible modulo compact operators. Equivalently, if this coset is invertible in this quotient algebra, equivalently, and this is now not trivial, an operator is Fredholm if and only if the image space is closed, if the kernel has a finite dimension, and the co-kernel, this is this quotient space, has also a finite dimension. The idea behind this is if we are in an infinite dimensional space, then a 500-dimensional kernel is nothing in comparison to infinitely many dimensions. So, and the essential spectrum is the set of all lambda such that this operator is not even Fredholm. And obviously, the essential spectrum is always a subset of the spectrum. The symbols case, for Laurent operators, things are very simple. If A is an L infinity function, then the spectrum of this Laurent operator and the essential spectrum of this Laurent operator is the essential range of A. Functions in L infinity are only defined almost everywhere, so one has to distinguish between the range and the essential range. If A is a continuous function, then the essential range is simply the image of the unit circle. So a result in this, I wrote the symbols case, but this is a very non-trivial result. It was obtained by Gochberg in 1952. He showed if A is a continuous function, then the essential spectrum is the range of A. Here you see the typical range of a continuous function. Our functions are all complex valued. That is, they describe a curve in the complex plane. Then the essential range is simply, the essential spectrum is simply the range of A, in this case the green curve. And the spectrum is the union of this green curve and of all lambda in the plane which are encircled by this curve with non-zero winding number. Here the winding number is 1, this belongs to the spectrum. Here the winding number is 2, belongs to the spectrum. Winding number is 0, and outside it is also 0. So you see what the spectrum and the essential spectrum is. This was for continuous function, but the most interesting functions are piecewise continuous. So let us denote by PC the closed algebra of all piecewise continuous functions, and the example is the Hilbert-Toeplitz matrix. This is a famous Toeplitz matrix, but also has a Hilbert-Hankel matrix, where here a plus sign stands. So the Hilbert-Toeplitz matrix is defined in this way. We can rewrite this in this form. So here you see the matrix written out once, minus, 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 and the same entries here, but with plus signs. The question is, what is the symbol of the Hilbert matrix? And it turns out the symbol of this matrix is this function. Look, if theta moves from 0 to 2 pi, then this right-hand side, first it is by pi I, and then it moves along a half circle to minus pi I. Theta is 0, pi I, and if theta is 2 pi, we have e to the minus pi I, and this is minus 1. So this is a piecewise continuous function. It moves along a half circle, and then makes a jump back from minus pi I to pi I. Here I have the computation that indeed the Fourier coefficients of this function are the entries of the Hilbert matrix. Here you have to compute this integral. This is the same as this integral. Here we have the function. If we insert 2 pi, we get minus 1. If we insert 0, we also get 1, but minus. And in the end, we arrive at this coefficient. So, what happens for piecewise continuous function? Here on the left, we see the result by Gochberg for a continuous function. The essential spectrum is simply the range of the symbol. In the 1970s, Gochberg and Grudnik showed that if we have a piecewise continuous function, and here you see a function continuous, here it makes a jump, again a continuous piece, another jump. Gochberg and Grudnik showed one has to fill in straight line segments to get a closed curve, and then the essential spectrum consists of this green curve and of the two red line segments here, and the spectrum are the numbers whose winding number with respect to this closed curve is non-zero. This was for individual operators. The approach to such theorems is, however, through algebras of operators. So in let us denote by Alk TC, the smallest closed subalgebra of the bounded operators in L2, which contains all Toeplitz operators. For example, if we have 5 continuous functions, then this is an operator in this algebra. Actually, we take all finite sums of finite products. This is a set, and the closure of this set is then this algebra. Gochberg proved his result in 1952 in the following way. He first showed that this algebra contains all compact operators, and the quotient algebra is commutative. So, and if we have a commutative algebra, it has one-off algebra, it has a maximal ideal space and a Gelfand transform, and Gochberg showed that the maximal ideal space is the unit circle, and the Gelfand transform maps this algebra to the continuous function on the maximal ideal space, and it maps such a coset simply into the value of the symbol at the point t of the unit circle. For instance, such an operator is Fredholm if and only if this condition is satisfied for t. The same now for piecewise continuous functions, and this was done by Gochberg and Grudnik in the 1970s. They showed again that this algebra is commutative. The compact operators are contained if we consider only continuous functions, so they are also more contained herein. And the maximal ideal space may in this case identified with this cylinder, but with an exotic topology. And the Gelfand transform is given in this way. Gelfand transform is a function from the algebra to the continuous functions on the maximal ideal space. And if we take a point T in T and a point X from this line segment, then the Gelfand transform is defined in this way. Clearly, if X moves from 0 to 1, this describes the line segment from the left limit to the right limit at the jump. So, all this was Hilbert space theory. We now move to Banach spaces. The little L2 is the same as the big L2. And we know the Laurent operator is multiplication by A. The little L2 are over the non-negative integers are the functions in the big L2 whose Fourier coefficients vanish for negative integers. And this is called the Harvey space, H2T. So a Toeplitz operator may therefore consider on the Harvey space in the following way. We take a function from the Harvey space, multiply it by A, and then project, we get a function in big L2, and then we project it back to the Harvey space P. P is the orthogonal projection of the big L2 to the Harvey space. If we represent a function in L2 by its Fourier series, then this orthogonal projection acts simply in this way. It takes only the positive Fourier coefficients. And now the Cauchy singular integral operator enters the scene. The Cauchy singular integral is formally defined in this way. We take the principal value and then this integral of a function f over the unit circle. You see as if t is a point on the unit circle and tau moves along the unit circle, then we here divide by 0, and so we have to consider the principal value with the hope to save something. It turns out this operator is really well defined and bounded on L2. And if we represent a function in L2 by its Fourier series, here I have changed the order. Here we have the negative Fourier coefficients, here the positive Fourier coefficients. Then it turns out that the singular integral operator maps this function into this. It keeps the positive part, but the negative part gets a minus sign. If you now add these two, then these cancel out, and we obtain 2 times this expression, and this is the Ries projection. In other words, I plus S is 2 times the Ries projection, the orthogonal projection so far. So this is our projection of L2 onto H2. We made it expressed in terms of the singular integral operator. And now the point is the singular integral operator may also be defined in arbitrary curves. Let us consider a curve gamma which is piecewise C1 plus delta, and it is a Jordan curve that divides the plane into 2 connected components. Here you see this blue curve is a Jordan curve, is a Jordan curve and a Lyapunov curve. Now fix a point on this curve and consider everything on this curve which is contained in a disk of radius epsilon. This is called the portion of this curve around T within the disk of radius epsilon. So, and the Cauchy singular integral operator, here I made precise what principal value means. You first take out this piece when integrating. You integrate over the rest. You do not divide by 0. And then you let epsilon go to 0. This is the singular integral operator. And Marcel Ries, around 1920, proved that the singular integral operator is well defined and bounded on LP if and only if P is between 1 and infinity. And so we will in the following consider LP spaces with P between 1 and infinity. You know what the LP space is. What is the Hardy space? The Hardy space is simply the range of P on LP gamma, and P may now be expressed via the singular integral, and not through Fourier coefficients or things like this. Everything is easy. And the Toeplitz operator is defined in the usual way. We first multiply the function by A and then project it back to the Hardy space. And this algebra now stands for the smallest closed subalgebra, which contains all Toeplitz operators, and I suppress the dependence on P. Metamorphosis 1. It turns out that the cylinder M we had so far now becomes a barrel, depending on P. This is the maximal ideal space of the algebra we saw on the previous slide. And this barrel results from letting a circular arc rotate around the unit circle, and it turns out this circular arc is given by this angle, and this angle is 2 pi over the maximum of P plus Q, where the exponents are related by this equation. If P is between 1 and 2, this arc has to be drawn on the right of this line segment, and for larger P it has to be drawn on the left. So that is, if we consider the algebra generated by the Toeplitz operators with piecewise continuous functions, then the maximal ideal space becomes this barrel. Was proved by Gochberg and Krupnik. Contains the compact operator, quotient algebra is commutative. The maximal ideal space is this barrel. And if we parametrize this Jordan curve by a function phi over t, then everything may be reduced. This is where the t here comes into play. If we would not parametrize, then the maximal ideal space would not be this barrel, but this circular arc would move along the curve. But anyway, the Gelfand transform is now given in this form, and the Gelfand transform of a coset, where t is a point on the unit circle. We take the value of a at phi of phi, we are on the curve, and here we have the x which fills in the line segment. And if we leave Hilbert space, then we have a problem of inverse closedness, and it turns out that an operator is Fredholm if and only if it is invertible in this algebra, that is, this algebra is inverse closed. Geometrically, it means now if we consider Toeplitz operators over arbitrary smooth curves, in particular over the unit circle, with a piecewise continuous symbol, we have no longer to fill in line segments, but we have to fill in circular arcs. So, now one can consider the operator not only in LP gamma, but one adds a weight here. The norm is given in this form, that is, we consider weighted LP spaces. Power weights are weights of this form. We fix n points on the unit circle and n exponents, and then we have such a weight. In 1956, Fredericks proved that the operator S is well defined and bounded on such a space if and only if the exponents we have here are between -1 over p and 1 over q. So, and this means this barrel now becomes a barrel with exceptional circular arcs. So this, at the point where the weight is sitting, we have to change the original arcs by new arcs. And the angle of these new arcs is now defined by P and the exponents. This means geometrically we have again to fill in circular arcs, but the shape of these circular arcs now depends not only on P, but it depends also on the weight. So, interim balance, we had L2 over a nice curve, cylinder LP over a nice curve, this parallel LP over a curve with right, this parallel with some things here. This was the state of the art in the 1970s. People thought now the matter is finished, but in 1990s, Witkowski came away and surprised the community with a great result. He considered Magnhub weights. Let gamma be again a nice curve, P between 1 and infinity, but let W now be an arbitrary Y. The question is, when is the singular integral operator bounded with an arbitrary Y? This question has been studied by many, many mathematicians for almost a century, and the ultimate result is the operator is bounded on this space if and only if such a condition is satisfied. At the first glance, this condition looks very strange, but if you are working in this field, then after some time you will get a feeling for this condition, and you will see it has a wonderful symmetry, and it is really nice to work with it. Okay, whatever this means, we have a necessary and sufficient condition for a weight such that the singular integral operator is bounded. Such weights are called Magnhub weights, and one writes W is in AP if a weight satisfies this condition. You might say, show me a Magnhub weight. Power weights are Magnhub weights if and only if this condition is satisfied. This is the result of Toeplitz. Here is a strange Magnhub weight. It is E to such a function. So, okay, what is this function here? Let's consider this on 0, 1. If x moves to 0, then the modulus of the logarithm goes to infinity. The logarithm of this logarithm goes still to infinity. And now we take the sign of this, so this we get an oscillating function. And we multiply this oscillating function by log x. This means we get a function whose oscillations become larger and larger. We multiply this by a real number alpha, and so we get this picture. And now we take the exponential of this. The oscillations remain oscillations, but if we here go to minus infinity, then the exponential goes to 0. And if we here go to infinity, the exponential goes here to infinity. This here, you see, a Magnhub weight. And the interesting thing is we multiply it by alpha. This alpha cannot be too large. Alpha times the square root of 2 must be less than this. If alpha is too large, then this is no longer a Magnhub weight. But if alpha is small, it is a Magnhub weight. These are very subtle things. So, and what Witkowski proved is the maximal ideal space is now a barrel in which certain circular arcs have to be replaced by horns. And this in the case of general Magnhub weights. Geometrically, this means we have now to fill in certain horns between the chunks in order to decide what the essential spectrum is. And the spectrum is, as usual, the set of points whose binding number with respect to this is 0. Okay, Witkowski did not speak about horns. Horns is a coinage of mine. This looks really like a horn, but we may also have such things where the circular arcs are very large. This does not look like a horn, but we nevertheless call it a horn. So this was the situation of Spitkovsky. So, so far we suppose that gamma is a nice curve, but the weight was arbitrary. Now another thing. What happens if gamma is a bad curve? For what kind of curves is the singular integral operator bounded in this space? Again, many people have worked on this. Calderon proved instead of C1 plus delta, Lipschitz is sufficient. And finally, Guy David in 1984 proved that the singular operator is bounded on LP if and only if this condition is satisfied. That is, the portion of the curve lying in a disk of radius epsilon must be at most a constant times epsilon. Such curves are called Collison curves or Alfors-David curves. Again, examples, as long as a curve holds logarithmically, it may be nearly arbitrary. Here we see a Collison arc, and one can always show if you have such an arc and you add another arc nearby, then you get a closed Jordan curve. This is a Collison curve. So I here give you some examples only of these arcs, and these may then be completed to curves. For instance, the following is a Collison curve. This scrolls up logarithmically, but it looks like an arithmetic spiral, because if I had drawn this logarithmically, you had not seen anything. For instance, it may be you have a curve, it moves in this direction 5 times, then in this direction 700 times, in the other direction 5 times, in this direction 13 times, 70,000 times in the other directions. As long as all this is along a logarithmic curve, this is a Collison curve. Or here we have 2 logarithmic spirals and a curve that oscillates between these 2 logarithmic spirals. This is a Collison curve. Here we have again a logarithmic spiral, and inside this curve we make the following. We scroll up like a logarithmic spiral and out. Scroll up like a logarithmic spiral and out. And we make this infinitely many times. This is a Collison curve. The singular integral operator is bounded on this curve. And if we now repeat this picture between a logarithmic spiral, we get such a curve. And the question is, what happens with the singular integral in such curves? And the longer you think about this problem, you see this is actually an abyss. What kind of curves may exist? Well, in 1994, we studied another problem. We did not consider such complicated curve like the one shown, but simpler class of curve, and we observed that the circular arcs we had in that case become logarithmic double spirals, and the horns of Spitkovsky become spiralic horns. This was for certain special Collison curves and not for general Collison curves. That is, our result was the maximal ideal space now becomes something like this. And geometrically, if we want to have the spectrum or the essential spectrum of a Toeplitz operator, instead of the line segments, circular arcs or horns, we now have to fill in such things between the endpoints of the chunks. But then we ask, what happens for arbitrary Collison curves? In particular for the monsters I have shown you in the previous slides. This problem solved with Karlovich in 1950 and 1995, and we observed that in this case we obtain so-called leaves with a separating point. Here you see such leaves. These are the endpoints of the chunks, the black dots. Here you have a 6 set, here a 6 set, and the separating point is in the middle between these two. This is a single point here. These are two sets. You have only a single point in the middle. These are leaves with a separating point. That is for operators with arbitrary Carlson curves. No weight. The maximal ideal space looks like this, and geometrically, to find the spectrum of the operators, we have to fill in such sets. Yes, make a photo, it's nice. We then thought, oh, this topic will feed us a lot of years in the following, because now let's consider arbitrary curves and arbitrary white space. Again, when is the operator bounded? Here you have many names. This theorem is the result of research lasting for 100 years. The operator is bounded on LP over a curve with a weight if and only if P is between 1 and infinity. The curve is Carlson and the weight is Magnhaupt. So consider an arbitrary Carlson curve with an arbitrary Magnhaupt weight. This Karlovich, unfortunately, within short time, because we thought this could feed us many years, within a short time we observed that in that case we obtain leaves, what we called leaves with a halo, and these look like this. I will now explain what this means, but let's recall. If the curve is nice and the weight is nice, we have circular arcs. If the curve is nice and the weight is general, we have horns. If the curve is arbitrary and the weight is nice, we have such things with a separating point in the middle, and if the curve is arbitrary and the weight is arbitrary, then this separating point disappears and it may thicken here. We obtain leaves with a halo. In general, that is, in the general case, this is the maximal ideal space, and to find the spectrum of the operator, we have to fill in such sets. This is the original paper where we published this result. The interesting thing is the paper was submitted in 1995 and it appeared only in 1999, but we mathematicians are writing for eternity, so it is 4 years. Here you have some pictures from this paper, were quite complicated. And I showed you here many pictures. I think you know there is some mathematics behind these pictures. In fact, this is a non-trivial thing. So let's conclude with the following. You have seen all these sets. The question is, what is the building plan for these sets? Here it is. We start with a green set. This is called the indicator set. We take a point, a number in this set, take the exponential, and then this Möbius transform. And the result we obtain here is the leaf. Here is the case where we have a nice curve and a nice weight, Kochberg-Rupnik. In that case, it turns out the green set is a horizontal line segment. Now take the exponential of a horizontal line segment. This horizontal line segment may be written as x plus I, 1 over p plus mu. If this is the same as this, if x moves from minus infinity to plus infinity, this moves from 0 to infinity multiplied by a constant. So this exponential maps this horizontal green line to a ray starting at the origin. And now we apply this Möbius transform. 0 is mapped into -1, and infinity is mapped into 1. And so this line segment is mapped into a circular arc between -1 and 1. This is the way the circular arcs of Rorberg and Rudnick arise. In the Spitkowski case, it turns out that the green set is no longer a single horizontal line, but it is a stripe, a set of horizontal lines. Each of these horizontal lines is mapped into a ray, and all these rays are mapped into a bundle of circular arcs, and we obtain a home. What happens if we have a spiralic curve and a nice weight? That's this situation, first observed with Karlovich. It turns out, in the case of a strange curve, this green line segment is no longer horizontal, but it gets a slope. So if you map such a line with a slope by the exponential, then you here obtain a logarithmic spiral. So and here, to this spiral, you apply a Möbius transform. The best way to imagine this is to think of the complex plane as the Riemann sphere, and then such a logarithmic spiral is something that scrolls out of the North Pole and then scrolls in at the South Pole. And this is, in this way, you obtain such logarithmic double spirals. And if we have an arbitrary curve in a nice way, then we have not only one line with a slope, but we have many lines with a slope. Each of these lines with a slope is mapped into a logarithmic double spiral. I here left out the blue picture. And all these double spirals who all go through this point. The union of these double spirals forms such a logarithmic leaf. Now, and if we have a spiralic curve and an arbitrary weight, then instead of a single line, we here have a bundle of lines, a bundle of logarithmic spirals, spiral on here. Yeah, in the final case, arbitrary curve and arbitrary weight. Arbitrary curve means we have here a lot of different slopes. Arbitrary weight means this is not only a single line, but these are many lines. We get here such stripes. Such a thing is mapped by exponential Möbius transform into something like this. But we could not prove that in the general case something like this emerged. We obtained that the green set is the union of this set and of these two sets. And these two sets are the following. We here have to fill in a convex function which has the same asymptotes here and here as these straight lines. And here we have to fill in a concave function with the same asymptotes as here and here. This is what we could prove, and these two pieces produce something we called a halo, because corona was already used in other contexts. Yeah, we could prove this happens. But what is the final result? The final result was the following. We could prove if we are given any convex function with such asymptotes and any concave function with such asymptotes, then there exists a curve and a weight such that just these two things appear. And this was the final result. In this way, we got the final solution of the problem. In other words, general weight plus general weight gives this, general curve gives this. One could think that such logarithmic leaves are the end of the story. No, it turns out there is some interference between the oscillations of the weight and of the curve that produces this halo. But we could describe completely this halo. All this is in this book written down in detail with many, many more examples. This was the book that got this prize, and at this point, let's stop. Thank you very, very much for your attention.
Thank you very much for the talk. Are there any questions or remarks? So, did you, sorry, if you call these sets halos because of the holes?
No, the halo is we have the sun, and around the sun there is something not such nice at the sun. This is the corona. I would like to call these additional pieces corona, but corona is in Banach algebra theory already used for other things. We have the corona theorem, and so I had to invent something else, and we called it halo.
Any more questions?
Entschuldigung, Deutsch werde ich fragen.
Ja.
Sie dürfen es nicht ganz im Ernst nehmen, was ich fragen werde, aber mich hat es also doch ganz tief betroffen, als ich das gesehen habe, Frobenius.
Ja.
Und da habe ich nachgedacht, also wie viele mathematische Leistung hat der Frobenius,
ja,
der Basler Drucker im 15. und 16. Jahrhundert. Und da war ich enttäuscht. Ich habe sehr schnell nachgeguckt, dass er ein Mathematiker war und um Ende 19. und 20. Jahrhundert. Aber Frobenius hat, also für mich war es also eine riesengroße Sache, dass ich endlich etwas verstanden habe, und das war Frobenius von Ihrem Vorlesung, Entschuldigung.
Das freut mich.
Aber sonst haben Sie keine, also nicht Sie, sondern die Frobenius Mathematiker und der ehemalige Basler Drucker, keine.
Ja, doch, das war also eine Generation, Frobenius, Minkowski, all diese Leute, also Dirichlet, es gibt da noch 10 Namen, mir fallen bloß keine weiter ein. Die haben also wirklich Erstaunliches geleistet. Das war wirklich eine Blütezeit der Mathematik, und Frobenius war also einer der ganz Großen von da, und ich zitiere ihn immer wieder gern. Gut.
More questions? If not, then thank you very much again.